In the last class we looked at a string with homogeneous boundary conditions and driven by initial conditions. Driven by initial conditions. Now we look at a string with again homogeneous boundary conditions, okay, but this time it is driven by a force, okay, and it has initial conditions, non-zero initial conditions. Initial conditions. Okay. So there is a force acting, okay, of the force acting of the form f of x comma t, okay, and then you also have w x at t equal to 0 is equal to w 0 and w dot x comma t equal to 0 is w dot 0 of x. Okay. I will try to see that my w's are big in the transformed domain and they are small in the original domain. Okay, I will try to do that. So now the forced equation for a string, forced string equation, okay. So we did have t del 2 w of x comma t del x square is equal to rho L del 2 w del t square, okay. So now if I put a force, it is going to be f of x comma t, okay, and if I bring the t down, okay, so I will bring the t down so that this becomes 1 by c square and here I have t the tension, okay. So again we go for a transform, okay, because the string is fixed on both ends, fixed on both ends. So we will do a series type solution. So we first take a transform, p is equal to pi into x by L when x equal to 0, p equal to 0 when x equal to L, p equal to pi. Okay. So now if we do that as before, we get pi square by L square del 2 w of p comma t by del p square plus f by t, but this is now a function of, okay, let me say p over here, or L p by pi comma t. Okay, I will just keep it as p, keep it as p, p comma t is equal to 1 over c squared del 2 w p comma t by del t square, okay. 0 p pi. Okay, as before we take a sine series. Okay, so that what happens is we have pi square c square by L square integral 0 to pi del 2 w of p comma t by del p square into sine n p dp, okay, plus this integral 0 to pi 1 over t f of p comma t sine n p dp, that happens to be equal to integral 0 to pi, okay. So the c square has to come here, c square, the c square is gone from here, del 2 w p comma t del t square sine n p dp. Okay, now we have seen this before. Okay, so I will write it straight away in terms of w n comma t. Okay, so that becomes d2 big W n comma t by dt square plus pi square c square n square by L square w of n comma t is equal to c square by t, this time it is f of n comma t. The same transform has happened on this, so it's f n comma t. Okay, now where, let me just say it, w n comma t is equal to integral 0 to pi w of p comma t sine n p dp, and f of n comma t is equal to integral 0 to pi f of p comma t sine n p dp. Okay, so this is just the simple harmonic oscillator with a forcing on the right. Okay, so what happens, let me just do this over here. If we had x double dot plus omega n square x is equal to 1 over m into a delta function, okay, then the impulse response, you may know, is given by 1 over m omega n sine omega n of t. Okay, one may recall. Then if I take this equation here, let me take this, if I take this equation over here, okay, then my impulse response, so called impulse response h of t is 1 over m, okay, so that is c square by t, okay, into omega n, which is L by pi c n into sine pi c n by L into t. If t is rho L c square, okay, if t is rho L c square, and c square goes, okay, so this is L by pi c n rho L sine pi c n by L into t, okay. Now from here, for any other function, what we have is the response x of t is the integral 0 to t, okay, f of tau h of t minus tau d tau, okay. So similarly here the response now w of n comma t due to this forcing, okay, is equal to L by pi c n rho L integral 0 to t f of n comma tau sine pi c n by L t minus tau d tau, okay. So now we include the initial conditions. Okay. So if we include the initial conditions, just as we do it for a spring mass system, the W of n comma t becomes equal to W0 of n cosine pi c n by Lt, okay, plus L by n pi c W dot n sine pi c n by Lt plus the forcing L by pi c n rho L integral 0 to t f of n comma tau sine pi c n by L t minus tau d tau. Okay. So we have come till the solution in the transformed domain or transformed variable. We have to get back to Wx of t, okay. So first of all, Wp of t is 2 by pi summation n equal to 1 to infinity W of n comma t sine np, okay. So now if we bring the W and t in here, my W of p comma t is equal to 2 by pi summation n equal to 1 to infinity w0 of n cos n pi c by L into t sine np plus 2 by pi square L by c summation n equal to 1 to infinity 1 over n w dot 0 of n sine n pi c by L into t sine np plus summation n equal to 1 to infinity twice L by pi square c n rho L integral 0 to t f of n comma tau sine pi c n by L t minus tau d tau into sine np. Okay. Now we have to bring it to x. Okay. If we bring it down to x, what we have is here w x comma t is equal to 2 over L summation n equal to 1 to infinity cosine n pi c by L into t sine n pi x by L integral 0 to L w0 of xi sine n pi xi by L d xi plus 2 by pi c summation n equal to 1 to infinity 1 over n sine n pi c by L into t sine n pi x by L integral 0 to L w dot 0 xi sine n pi xi by L d xi plus summation n equal to 1 to infinity twice by pi c n rho L sine n pi x by L 0 to t integral 0 to L f of xi comma tau sine n pi xi by L d xi into sine pi c n by L t minus tau d tau. Okay, so that's the solution with a forcing homogeneous boundary conditions and initial conditions. Okay. Now the next problem we will do is again a fixed string, okay, but this time no initial conditions, or initial condition effect is died out, okay, they are not important, they have died out, and it is driven by a point harmonic force, okay. I suppose the fixed string, fixed at two ends, it is driven somewhere by a harmonic force at x equal to x0, and initial condition effect is over. So, we are looking at a steady state response, steady state harmonic response. Okay. By fixed we mean the boundary conditions are homogeneous boundary conditions. Okay. So, the equation we have seen, so it just modifies a little bit. So, what we have now is the del 2 w of x comma t by del x square plus f by t delta x minus x0, okay. This is how the force gets located, okay. E to the power j omega t is equal to 1 over c square del 2 w by del t square x comma t. Here x is bounded between 0 and L, okay. So, now what we have here is this the mode shape, okay, is given by w n of x is sine n pi x over L, okay. This is the mode shape. Why? Because it satisfies the homogeneous condition on both ends, okay. And then we assume that the displacement can be expanded, okay, in terms of this modes as a weighted sum. So, we have a n w n of x e to the power j omega t, because forcing is harmonic, okay. So, now if we substitute, so the assumption is that the mode shapes form a complete set, okay. That means they are capable of representing any displacement the string may happen to acquire during its vibration, and the more number of terms you take, the more accurate your representation becomes. And they are also orthogonal, modes are also orthogonal. Okay, these are the two properties that these mode shape functions have. Okay, so now okay, let me okay, so now if we now substitute this expression up there, okay, what we get is del 2 by del x square. Okay, I just want to do one simple calculation before that. Okay, you might be wondering how I am getting this sine n pi x by L. So suppose I have del 2w by del x square x comma t, okay, and that is equal to 1 over c square del 2w by del t square x comma t. Okay, now I am going to excite it harmonically, so my w of x comma t will be some capital W of x e to the power of j omega t. Okay, and if I substitute in here, I get d2 w dx square plus k square w equal to 0. Okay, this is the double derivative on space, so double derivative on space, e to the power j omega t will cancel from both sides. Double derivative brings me a minus omega square here, which becomes a plus k square here, and then w of x and e to the power j omega t I cancel from both sides. This again like the simple harmonic oscillator, except it's in space. So this is a Sturm-Liouville problem, LOUI, Sturm-Liouville type problem, and they have, these are wonderful theorems, and one should look at what are Sturm-Liouville problems. This is one particular case of that. Okay, and so the solution to this is w of x is equal to sum a cos kx plus b sin kx. Okay, then what I say is w at x equal to 0 is 0. Why? Because my string is fixed. So if I put x equal to 0, this is gone, and I get a equal to 0. That means my w of x is b sin kx. So I have the mode shape. Then the other boundary condition, w at x equal to L equal to 0. So that means b sin k L equal to 0, which means k L is of the form n pi, n ranging from 1 etc., because 0 gives a trivial value. That means k is n pi by L. That means my shape, mode shape now as an n index is sine n pi x by L. So you see how this comes about. Okay, so now we are going to substitute this in here and see what happens. So if we do that, what we have is del 2 del x square summation a n w n of x e to the power of j omega t plus f by t delta x minus x 0 e to the power of j omega t is equal to 1 over c square del 2 del t square summation n from 1 to infinity a n w n of x e to the power of j omega t. Okay. Now we said these mode shapes are orthogonal. So Wn and Wm will be orthogonal to each other. So what we will do is we will multiply both sides by Wm. Okay. So what we have is let us see, summation n to 1 to infinity a n w n double dash, meaning double derivative with respect to x e to the power j omega t. I will cancel from all sides. Okay. Then I will bring okay, I will use the derivative before I cancel. Let me use it. So we had e to the power of j omega t e to the power of j omega t. So this time derivative acts on that. Okay, e to the power of j omega t, then plus f over t delta x minus x naught e to the power j omega t, that is equal to, time acting on this gives me minus omega square. So minus k square summation n a n w n of x e to the power j omega t. Now I cancel because it never goes to 0. Okay, I will bring this term to this side and forcing to the other side. Okay, and then I will multiply by w m of x, a different index. Okay, so what happens? I have summation n going from 1 to infinity a n, okay, integral 0 to L k square w n of x plus w n double dash of x, and I multiply by a different mode shape, and I do the same on the right, minus integral 0 to L f by t delta x minus x naught w m of x dx. Okay, just want to make one point here, which is that in the string equation when you put a force, okay, the force by itself has to be force per unit length. Okay, so if you just put a force, if you just put this expression f, okay, as we did for the earlier case, where was that? Here, this force has to be force per unit length. okay, that is when the units fit. So now what happens here is that this delta has a 1 over length unit. So automatically you are getting per unit length. So then this has to be full force units, full force units. I just wanted to mention that. So you have to adjust the force to match the description, okay. It is a point force, so you have to describe it like that, okay. So now we are here, okay. So now let me just show you that what W double dash of n of x is from here. It is just minus n pi by L whole squared into W n of x, okay. So that is the advantage of having a mode shape, okay. The derivative has become algebraic. It was a derivative, you wouldn't know what to do with it, okay. But because it is a mode shape and it satisfies the boundary conditions and it is an eigenfunction having an eigenvalue with it, the double derivative of that has ended up like this. That is the beauty of the whole thing, okay. So now what happens is we have summation n equal to 1 to infinity a n integral 0 to L, okay. So now because this has become a constant into the mode shape, I will take it outside, k square minus n pi by L whole squared, then W n of x W m of x dx, and on the right I have minus f over t W m of x naught, which is the delta function property, okay. So I will just call this k n squared, okay. So now what I have is summation n equal to 1 to infinity a n k square minus k n square, okay, let us say capital, integral 0 to L W n of x W m of x dx is equal to minus f by t W m of x naught. Now if I have an integral 0 to L sine n pi x by L sine m pi x by L dx, this is equal to 0 if m is not equal to n. And what is it equal to when m is equal to n is I have sine square n pi x by L, which is integral 0 to L 1 minus cos 2 n pi x by L by 2 dx, and this integrates to 0 over 0 to L. So I get L by 2. Okay. So I will just represent it, I will not write gamma L by 2, I will call it gamma n. Okay. So I have now, so what has happened, if I put an arbitrary m, but unless it is equal to n it does not work out. So this n has to match m, so one of this is picked up, there is no more a summation. So that particular value of n which is equal to m, okay. So m and n are equal. So I have a n, the series is gone, or the summation is gone, k square n gamma n, I put gamma n because it could be any constant. Sometimes when the n goes to 0 versus n not equal to 0, it has different values, so I put a gamma n, whatever it comes out, Here it is not a problem because the summation n goes from 1 and not 0. Okay. If you had a cosine, you would have a problem because n 0 will have a different integration, gamma n will differ. Okay. So, this is now equal to minus f by t w, everything is n now because n is equal to m, and a n is equal to f w n of x naught by t k n square minus k square gamma n. Okay. So, a n has been found, the one that we did not know. Okay. So, we had expanded in this form, the unknown we had expanded, these are mode shapes, these are coefficients of the mode shapes. So, a n was what was to be found, and a n we have found now, okay, that is the n. So, my response finally is equal to summation n goes from 1 to infinity. Okay. I suppose gamma n value we can take as L by 2. So, 2 over L f sine n pi x naught by L, where the force is being applied, then rho L okay, let me keep it as okay, rho L c square into k n square minus k square. Okay. Now, I can bring in c square inside, one more step, w of x comma t is equal to summation over n from 1 to infinity 2 over L force per unit length sine n pi x naught by L. Here there is a sine n pi x by L e to the power of j omega t, and n pi x by L divided by c square, I take it inside. So, what I will have is rho L omega n square minus omega square into sine n pi x by L e to the power of j omega t. And this is the driving frequency, okay, of the harmonic force. So, anytime omega x gets close to any of the natural frequencies, your response goes up. So, that is resonance. Okay. So, now we have what? A steady state response to a string subjected to a harmonic force, single frequency force, harmonic point force, and with homogeneous boundary conditions. Homogeneous boundary conditions. I will close the lecture here. Thank you.